Hello everyone, so far we have looked at what the climate actually is, and we've seen how the climate has changed over the past million years or so. Today, or now, we're going to look at where do we get the evidence of climate change? Where do we get this evidence that our climate is currently changing? And we're going to see the different ways that we record and can collect this data. So there's 10 main indicators that we can use, and we measure things about these indicators to see the changes that are happening. Most of these are to do with temperature, so we've got temperature over land down here, the air temperature, the temperature over oceans, the heat content in the oceans, and the sea surface temperature. These things are direct measurements of temperature. Now, some of these things are definitely related to temperature, so for example glaciers. If we have less glaciers or the size of the glaciers is getting smaller, then we can expect it to be a warmer atmosphere. Likewise, snow cover and the amount of sea ice we get. Humidity is also linked because if we get warmer temperatures, we get more evaporation. If there's more evaporation, we're going to have more moisture in the atmosphere, which increases the humidity. So the first thing we'll look at is how we record glacier and ice sheet changes. An ice sheet is basically a layer of ice that extends over 50,000 square kilometers, covering an area of land. And the two main ones we've got are in Antarctica and in Greenland. And since 1992, we've used satellite measurements to record how these ice sheets and how these glaciers are either shrinking or expanding. And basically, in a period of 19 years, from 1992 to 2011, all polar regions, so towards the North Pole and Antarctica, are losing ice. And there's a few absolutely staggering statistics here that Greenland lost 152 billion tons of ice each year. West Antarctica lost 65 billion tons a year. The Antarctic Peninsula, 20 billion tons a year. And only one place gained ice, which was East Antarctica, getting 14 billion tons a year. So the pattern is that huge areas of the world are losing a huge amount of ice every single year, which would indicate that the world is getting warmer. And we can see these changes in the amount of ice quite clearly here. We've got three photographs, this one here, and here, and here, showing ice sheets breaking up and the ice drifting off into the sea. And in this bottom right image here, we can see the Larsen B ice shelf, which had a huge collapse in 2002. Basically, within a month, or just over a month, scientists watched with their satellite imagery and recorded this photos just like this, and they saw 3,250 square kilometers of solid ice shelf like this disintegrate and basically fall into the sea, becoming these icebergs. And now this bay is completely free of ice, as all of this ice that was left here has basically been washed away and moved away by the currents, and some of it has melted. As a result of these changes, we can see that Antarctica has actually lost a huge amount of ice. These measurements taken by satellites, looking at how much mass of ice there is in Antarctica, show that since 2002, which is here, the general trend has been a decrease in the amount of ice. And if we look at this number here, that's 134 gigatons of ice lost per year. Now, a gigaton is a billion tons, so that is 134 billion tons of ice lost every single year on average, okay, which is a staggering amount of ice that is being lost. And here we can just see one of the satellites that NASA is using to collect information on climate change. On this slide, we can see how glaciers in mountainous regions have been changing over time. And when glaciers move backwards, it's called glacial retreat. So this word here, okay? Here we can see some changes. Here's 1985, this is 2007. You can see this area here, this is the snout of the glacier, or the end of the glacier. And this photo is taken from the same position. You can see that the snout of this glacier has moved back up the valley to approximately this point here. Okay, so the glacier has been melting faster than it's been coming down the valley. So the overall effect is that it seems like it's going back up the valley. We can see that even more drastically on these photos on the right-hand side of the Muir Glacier. So here's 1941, and the picture at the bottom is 2004. And if we match up a few features, it can start to help us see the changes that have taken place. So if I try to identify that mountain there, it's that mountain there. This mountain here is this mountain here. This truncated spur probably is that bit there, and it comes down here. And this arête or ridge coming down is that one there. Okay, so this whole area, which is now a huge lake, was in the past all ice. These changes have taken place over the last 63 years. That is an astonishing amount of melting that has been taking place. And this is all to do with a balance between two things. The first thing is ablation. Ablation basically means the melting of the ice in the glacier. And the second thing is accumulation. So when it snows, it takes about 25 years for that snow to compress down and form rock-hard glacial ice. Okay? And then at the end of the glacier, in the summer, we get melting. So if there is more accumulation than there is melting, the glacier is going to grow in size. But if there is more melting, ablation, than there is accumulation or snow falling at the top and becoming glacial ice, then we're going to get glacial retreat. So in this case, we've got more melting, so we'll do a plus there, then we've got accumulation. Okay, and the more melting is a result of warmer temperatures. So as the Earth warms up, we get more melting taking place, and therefore our glaciers are shrinking, or, as we mentioned earlier, retreating. Obviously, one of the really important things to measure is just the temperature. And since 1880, we've had pretty accurate records of global temperatures from thermometers, but more recently we've been using obviously the land-based temperatures and the sea temperatures from those thermometers, but also satellite data to give us an indication of temperature changes. And again, the pattern is pretty obvious. We start down here, we end up here. You know, we have a bit of a fall here and a bit of a rise and a bit of a fall, and then it just keeps going steadily up. Okay, so overall the temperature is increasing. And data from that graph can be plotted on a map, as has been done here. This is showing the changes in sea surface temperature between 1901 and 2014, so 113 years. Now, it should be very obvious to see that most of the colours are reds and dark oranges. There's a couple of areas of browns down here and down here, down here. And if we look on the key, we can see that into the reds and the browns and oranges is going from basically a 1 degree change in sea surface temperature up to the highest is probably getting around 3 degrees Fahrenheit warmer. Okay, not Celsius, sorry, it's definitely Fahrenheit as shown there. Okay, so overall temperature is actually increasing quite a lot in the sea. There is one striking anomaly here, which is just off the coast of Greenland here, and that is an anomaly because it is really the only part of the world where the sea surface temperatures have actually decreased. And one reason scientists think this is happening is because there is a lot of meltwater coming in from Greenland, which is this large mass of land here, which has a huge ice sheet on it. Lots of that is melting, and they think that that meltwater going into the sea is causing the temperatures here to decrease. However, the rest of the world, where there is data, is showing an increase. And this map shows the temperature changes of the land between 1901 to 2010. And what they've done here is they've taken the average temperature from 1901 to 1920, and they've taken the average temperature from 1990 to 2010, and then compared the differences. Okay, so they've basically taken this number, so one from here, and then one from here, and they've minused them. So let's call that one x, let's call this one y. They've done x minus y equals the change all right? And then they've plotted all that information onto the map. And we can see, again, using the key at the bottom down here, that most areas of the world are experiencing warming, and some places are experiencing really very significant warming. So northern parts of Canada, parts of central China into northeastern Russia, parts of North Africa. Okay, these parts of the world are warming on a really significant scale. Another thing we can look at to give us indications of a warming world is sea level rise. There are two causes of sea level rise. One is when the ice melts, it adds more water to the oceans. The second cause is related to a thing called thermal expansion. Thermal meaning heat, and expansion meaning taking up more space. So as the temperature of the oceans increases, as we saw in the previous slide, the water in it takes up more space. So basically we've got an expansion of the seawater, and that expansion is causing the sea level to rise as well. Okay, so we've got two things: more ice melting, adding water, and secondly, thermal expansion. Both of these things combined create something, and this is a very technical term, something called eustatic sea level rise. Okay, which is to do with the absolute rise of sea level. How do we know sea level is rising? Well, first of all, we can use satellite data, and this data from NASA is from 1993 to the present day, and they've recorded changes, a gradual rise of sea level, and the rate of change is approximately 3.4 millimeters per year. Now that might not sound like much, but over a long period of time that will very quickly add up. For low-lying communities, it is actually something that is already presenting quite a major challenge to deal with. The other way that sea level rise is being recorded is from tide gauges. Here we go, coastal tide gauges. And we can see since 1870 up until 1990, sea levels have been rising steadily from 0 millimeters of change in 1870 all the way up to nearly 200 millimeters of change. So in the space of 130 years, we've seen a sea level rise of almost 200 millimeters, which is equivalent to 20 centimeters, and that is taken from data all around the world. This slide just shows how that tide data is collected. We can see here we've got a solar panel and we've got some weather information data, and so that can send the information back to a computer system. And on the right hand side on this diagram here, it just shows how it works. We have a little gauge here. As the tide level rises, this gauge goes up. As the tide level falls, the gauge comes down, and basically that data is recorded. Now over the course of a day, I'll zoom in so we can make it a bit bigger and see it more clearly. Here we go. Over the course of the day, you'd go low from low tide to high tide to low tide to high tide, and that continues here. You can see the 10th of October, the 11th of October. If we're expecting to see sea level rise, then the data we would get from tides over a long period of time would start to change, and that change would be that the data we're going to record is going to show that this line starts to rise up a little bit to show higher tides, and that would continue day in, day out. And obviously I've exaggerated it a little bit on here to make it more obvious, and it would only be creeping up a very, very, very small amount, but tide data around the world will show us these patterns, and when it's all put together, it gives us a really good picture of what is happening to our sea levels. So there we have it. Hopefully that covers where we get evidence from to show that climate change is happening. Make sure you've got your notes written down, and make sure that you include some of the examples and the data, which really helps you to exemplify and develop your answers when writing about this topic.